Hello everyone. Today we meet again to discuss on the same topic, X-ray tube and generator. In the previous topic, I have briefly introduced the general components that make up an X-ray tube and X-ray generator. In the second part of the lecture of the same topic, I would like to go a little bit more deeper. Not deeper per se, but I would like to discuss more information about X-ray tube and generator for better understanding on how the different parameters, component, design of X-ray tube and generator makes up an X-ray machine or general radiography system, or an X-ray tube for memo, or an X-ray tube for fluoro. And before we begin, I'd like to acknowledge that some of you guys have started to pile in question to me in regards to this lecture. I'm not gonna reply to everyone individually. I will try and respond in general to everyone so that everyone can benefit from the answer. One thing for sure, thank you for all your questions. In the first section of the topic, I have introduced or explained about target angles and how does it affect anode hill effect. The anode angle basically refers to the angle the target surface of the anode sits in relation to the perpendicular angle perpendicular to the filament. So most X-ray tubes would have an angle at about 7 to 15. The higher degree angle or the lower degree angle is set depending on the application. Of course, the degree angle is much lower for mammography X-ray tube, for example, so that the effective focal spot size is small to provide better spatial resolution. The idea of a target angle or an anode angle is to provide a smaller effective focal spot size for better resolution. But these actually limit the size and the usable X-ray field provided by the X-ray tube. Therefore, an optimum anode angle must be utilized to provide high intensity X-ray and prolong the lifespan of your X-ray tube. In X-ray tubes, the Hill effect or anode Hill effect is a variation of intensity across the X-ray exit window. Due to the geometry of the anode, X-ray emitted towards the cathode side in general is more intense or produced at higher intensities than those emitted perpendicular to the anode axis or the anode side of the X-ray tube. The effects stems from the absorption of X-ray photons from when they leave the anode at where the X-ray is produced. This absorption is depending on the distance that the photons need to travel within the anode material, which in turn depends on the, of course, direction of the emission. A filter is normally installed in an X-ray tube to compensate the unevenness of these in X-ray field intensity. And this filter comes in varied thickness from the thicker side at the anode end and much thinner side at the cathode end. Another way of overcoming anode Hill effect is by positioning thicker portion of a patient near the cathode side of the X-ray to compensate this Hill effect. Let's have a look at this diagram. As the electrons being accelerated towards the positively charged anode through Bremsstrahlung or characteristic way of producing X-rays, electrons will hit the target. Although only 1% of the electron that will produce X-ray, most of the electron will just hit the anode and produce heat. So the 1% that hit or impinge on the anode that produce X-ray will be hitting the anode target at various depths. Those that are produced near to the surface will have to overcome a shorter distance to reach the exit window. Those that are produced deeper in the anode angle or the anode target will need to overcome a higher or longer travel path before it can reach the exit window. So that is one of the reasons why the intensity is much lower at the anode side. The second reason is because when the X-ray is produced within the anode target, say at the same position, depending on the direction of the emission, if the emission is directed towards the anode side, it needs to overcome just a small distance or to penetrate through just a small length or travel path within the anode. However, the same X-rays at the same location will, if it has to be emitted or if it's being emitted towards this direction, towards the anode direction, it has to overcome a much longer travel path. So these circumstances will create uneven intensity within the anode target. So that is the reason a filter is inserted to even out the intensity so that the intensity that will reach your patient or any subject matter per se will be even. Alright, let's have a look at this diagram to understand on the electron beam field, focal spot size field, and effective focal spot size field. So this is a schematic diagram on an anode target that is designed at an angle. This is the size of an electron beam coming from the cathode filament. However, because the target has been designed in an angle, it enlarged the surface area, so the electron can hit a surface area larger than its electron beam field. And this is then corresponding to the effective focal spot size at where it produces X-ray on an exit from the window. So just imagine if this anode target is designed at a reduced angle. You would notice that the focal spot size will be significantly reduced and will significantly further reduce the effective focal spot size. Thus, this is the reason why focal spot size or effective focal spot size is highly dependent on the anode target. In short, the effective target area or the effective focal spot is a measure of the width of an actual focal spot projected along the central ray and perpendicular to the plane of the X-ray port. as with the actual focal spot, the size of the effective focal spot is determined by the size of the filament and of course the angle of the anode. It is a requirement to report in a QA and QC measurement to report the effective focal spot size, in which this is essential because it is a measurement of the resolution that can be afforded by that particular X-ray tube. In general, the smaller the effective focal spot size, the better the resolution is. Effective focal spot size commonly used in diagnostic radiology range from 0.6 to 1 millimeter for small focus and 1.2 to 2 millimeter for large focus. So if we look at this diagram without a filter, the compensating filter, the intensity at the anode side is higher, that allows higher penetration. That the intensity at the anode side is lesser, that allows lesser penetration, that's suitable for subject matter with reduced thickness or low density subject material and so on. Let's have a look at this diagram. The angle at which X-ray emerge from the target surface toward the patient varies. The intensity varies and cause some X-rays to be absorbed in the heel of the anode. The heel attenuates a portion of the X-ray beam that produces X-ray at lesser intensity, leaves less intensity, leaves or produce X-ray photons with less intensity on the anode side of the patient. How do we make use of anode heel effect? When body parts of different thickness and density are being imaged, the heel effect can be used to its advantage by having the thicker part of the patient. So in this example, we are interested to, well, the photo isn't right or does not represent a true human being. Say that we are interested in the subject matter of this area, at where you can see the density of the bones are of course higher than other extremities of lower abdomen and lower of the upper abdomen. Because this area of the human being possess a high density tissue, the body parts at this body part is positioned at the cathode end, so we don't position our patient on the other way. The heel effect can be used to advantage if the cathode portion of the beam is placed over the thickest part or the higher density part of the patient. And it's good to note that heel effect is less noticeable with smaller film size and longer tube distance. So because more of the central uniform portion of the beams can be used. So if you have tube to patient distance that is shorter, you can only make up a small usage of this central beam. But if the source or tube to patient distance is higher, you can make bigger use of the central X-ray, that is 100% in our example. Let's look deeper into the definition of anode target, focal spot, effective focal spot, and anode angle. Target is where the electron hit the anode, so these are both targets. The actual focal spot is the physical area of the focal tract that is impacted by the electron. So where is the actual focal spot in these two diagrams? The actual focal spot is this area. The focal tract is portion or the bombarding electron beam. Focal tract, portion of the anode that the electrons bombard. On rotating anode, this is actually on a circular path. So that is a focal tract. So depending if it's stationary or rotating. Then we have effective focal spot. The same electron beam. So we have the same electron beam field at two different anode angle that produce two different focal spot size will produce a different effective focal spot. Effective focal spot is the area of the focal spot that is projected on the exit window. So those are the basic definitions of what are taking into consideration in anode Hill effect. Okay, let's have a look at this diagram, right? How does anode target angle define Hill effect? When the angle of the anode is greater, the usable X-ray photons will not have to travel through as much of the anode material to exit the tube. Therefore, it results in much less apparent anode Hill effect. However, the effective focal spot size is increased and that will decrease the image quantities, but that's later on. So let's focus on the Hill effect itself. Although beam does not come in lines, so let's say I quantify the X-ray beam into 5 lines. So there are 5 X-ray beams. Although we cannot quantify that in number, but for this explanation I will. So this is a much bigger focal spot that produces larger effective focal spot. Notice that only one beam has to overcome this distance. The second beam has to overcome a much lesser distance. The third beam has to overcome a much lesser distance, and it goes on with the following beam. The distance that the beams need to overcome is lesser if the anode angle is higher. However, for this anode target that produce a good effective focal spot size, produce good resolution, 1, 2, 3, 3 of the beam has to overcome a full length or a great length within the anode target. That will significantly absorb the produced X-ray. So in short, photon beams, X-ray beams produced with X-ray tube with smaller effective focal spot size will have higher or greater anode Hill effect. So I hope we get this right. Now that we fully understand what anode Hill effect, what effects is, how can we have a solution to overcome this? Almost all modern diagnostic X-ray machines exhibit Hill effect at some degree because anode is designed at an angle. It affects on image, the image quality, and this can be avoided through many considerations. One of it that I've explained earlier, by patient positioning. For example, when imaging a foot, the thicker part is at where the ankle is. The ankle is positioned towards the cathode side, and the toes with thinner subject should be positioned towards the anode side. There are also other methods to do it. Number one is by using compensating filter, and you can use a software adjustment to correct the pixel value, so the intensity is factored to a value to correct the uneven uniform X-ray field. And another way of doing it is by increasing the source to image distance. If you have an image receptor, be it a CR plate, a digital receptor, a film screen, here the image receptor will have an overfield from this intensity, the lower intensity, up to much higher intensity. It feels or it received X-ray beam at varied intensity. However, if you increase the signal to image distance, this image receptor of the same size feel the ununiform beam, but only from the small intensity up to the medium intensity. They don't feel the greater difference of the intensity. So this extreme intensity is not received by the image receptor. So therefore, if the signal to image distance is low or small, you can feel more Hill effect. If your signal to image distance is higher, you would feel less Hill effect. And the other physical method to overcome this is by using a much smaller field size. This is done via collimation and so on. If you have a small field size of that particular region of interest, your field size will only receive intensity from this intensity up to this intensity, and this is the central ray. A larger field size will have to receive an ununiform X-ray beam field from the lowest intensity up to the highest intensity. So a higher field size will have to accept or receive more Hill effect expectedly. So it is better for any acquisition, image acquisition, for the signal to image distance to be larger and the field size to be smaller, so that we are not affected by the Hill effect. In the first introduction, or the introduction of the generator, we also have a look briefly on the components that make up a transformer, and I did explain that a transformer is the component that is needed to manipulate the 240 volt power point supply to supply the circuitry of the X-ray tube and the circuitry in the filament, the X-ray filament circuit. And the AC is modified with rectifier. It's either full wave rectifier, half wave rectifier, to produce a direct current so that we do not destroy the X-ray tube. So let's have a look into this a little bit more deeper. Power supply is supplied to X-ray tube because X-ray tube require electrical energy for only two primary purposes. One is for the filament to boil off the electron from the filament, and second is to accelerate this electron. And these two circuits run at a complete different voltage supply. It's from 70 or 40 from MO to 150 kV for the acceleration of electron from cathode to anode, but up only to 10 volt to the filament. So in here there is the need of a system to modify the voltage supply by the generator. An X-ray generator uses direct current as opposed to the supplied current in AC. So the AC has to be rectified with a rectifier circuit, and this makes the sine wave to a series of humps. Modern X-ray machine use three-phase power supply, in which there are three series of voltage humps, each displaced about 120 degrees from another, which are added together to create more uniform voltage supply. Alternating current, or simply AC, is a type of electrical power in which the electric current changes in period of time, both in magnitude and direction. AC can be delivered either as a single phase or a three-phase. So what does phase means? AC power system consists of two wires, the phase, or sometimes called line, and neutral wire. So there are two wires. In three-phase system, you can use up to 3 and 4. No neutral wire is needed in this phase power. In a single phase power supply, the power is distributed using these two wires, and the AC power takes the shape of sinusoidal wave. The voltage in a single phase supplies and peak at 90 during the positive cycle, and then peak again at 270 during the negative cycle. The phase wire carries the current to the load, and the neutral wire provides the return path. So usually, depending on where you live, the voltage is up to 230. In Malaysia, we're running on 240 in 50 Hz frequency. Since the voltage in a single phase power supply rises, peak at 90, and then decrease and peak again at 270, a constant power cannot be supplied. So you have uneven supply of power to your X-ray tube if you're running on a single phase power supply. Heavy loads industrial machines like the X-ray machine cannot really be run on a single phase power supply, and there is where the three-phase power supply comes in. A three-phase power supply consists of 3 power wires or 3 phases. Depending on the circuit, you might not have a neutral wire. In the three-phase power supply, the load of the power is divided into 3. Each AC power signal is at 120 degrees apart from each other. In a three-phase power supply, during one cycle of 360 degrees, each phase would have peak in the voltage twice. So this is the first peak, and this is the second peak. First peak, second peak, first peak, and second peak. Also, the power never drops to zero. As the power of the first phase reduces, the second phase comes in, and the power supply goes back up. As it's trying to go to zero, it reduces its power. Another phase is supplied to make up of the loss. Therefore, the power never drops to zero, and this steady stream of power and ability to handle higher loads make three-phase supply suitable for industrial commercial operations, including X-ray machines. The efficiency of a three-phase power supply is significantly higher than a single-phase power supply. Single-phase power supply uses only 2 wires. The overall complexity of the network is less. However, when compared to the power supply, it's a winning for a three-phase power supply generator. Okay, let's go back to physics at where how do you generate electricity using magnet. Okay, EMF or electromotive force, EMF, electromotive force, works on the principle of Faraday's laws of electromagnetic induction, in which states that when a moving conductor, so if this conductor is moving in and out, in between the magnetic field, so there is the presence of a magnetic field, a force is produced in the name of EMF, or electromotive force. EMF is the force to move electron in any conductor, and it helps to flow the current in the conductor. So the Faraday laws of EM, or electromagnetic induction, is about magnetic field, and it proves that EMF, electromotive force, is produced in a moving conductor. This is a moving conductor when placed in a magnetic field. Faraday's law of electromagnetic induction can be understood or divided into two. Number one, when a conductor cuts a magnetic field flux, so there is the presence of a magnetic flux here, and when a conductor cuts the flux, an EMF is induced within the conductor. And the second law of Faraday explains that the rate of change in the flux, how fast or how slow the flux, the magnetic field flux is changed, determine the magnitude of the generated EMF. Alternating current generator is an important application of electromagnetic induction, and AC generator is actually used in X-ray machines or modern X-ray machines. So how are these AC current generated? So now that we understand how EMF is produced, let's imagine the positioning of magnetic field with north and south, with coil that is positioned perpendicular to the magnetic field. So the coil is positioned perpendicular to the magnetic field. This means that the sides of the coil, which are moving parallel to the magnetic field, actually not cutting through any magnetic field line. So these are the coil lines, and this is the magnetic field line. So the coil line is parallel to the magnetic field, so it is not cutting any magnetic field, so therefore there is no EMF, no electromagnetic force. So once the coil turns to a position at 90 degrees, the sides of the coil that moving perpendicular to the magnetic field will be cutting through the magnetic field lines at the greatest rate. So when it gets to here, the coil line is in this direction, and the magnetic field works in this direction. It cuts the magnetic field at the greatest rate. Hence, the induced EMF is at the maximum at this position. So as the coil moves from this position to this position and gets to this position, the rate the MMF produced is at the greatest. And then when the coils turn again and it reach this position, it goes back to 0, and then it increases again, and then it will reach the second peak before it decreases again. So that's how you generate varied EMF as you have a conductor moving and cutting electromagnetic field flux. Coils gets turned to reference position at 180 degree and 360 degree, 90 degree, 270, and so on. So now we understand how the voltage, the alternating current is, how does it work, and how does the alternating current works. The other way of doing it is not by having a moving conductor or coil, but by having moving magnetic field. So stationary coil then cuts the magnetic flux of the magnet, and as these two magnets are turning, this coil will cut the magnetic flux at different directions. So you will generate EMF at various intensity. So when they are aligned, the magnetic field and the coil line aligned or parallel to each other, the EMF will be 0. So how does the three-phase electrical system work? Is by having 3 coil or conductor that is positioned at 120 degree apart with a rotating magnet around it. So that's how you create a three-phase electrical system with alternating current. So in a short summary, how does the three-phase works? So now you have a magnetic field moving from this direction, and the coil cuts the magnetic field at the greatest rate, maximum perpendicular at 90 degree. Then you get to see the red phase is at its peak. As the magnet turns, it will then reach to this point at where the yellow coil or conductor will cut the magnetic flux at the maximum grade, and then yellow will peak, and then the magnet keeps turning until it reaches this position at where the coils, the current or the coil cuts the magnetic field at its greatest rate. So magnetic field flow from here to here, and then the conductor current moves from here to here. Then you get the peak for blue. This is a simplification of how three-phase alternating current is generated and how the system is designed. The induced EMF of all these coils represent the three phases, and the time displacement between one and another is taken into consideration. The coils that are physically 120 degree apart from each other with a moving magnetic field that is rotating at an equal speed generate EMF, but it is necessary for the total EMF at each point equal to 0 so that the circuit or the system can be designed in such way. This is called as a delta connection. So if you look here at this particular point, the positive EMF is 10 and the negative EMF by the yellow EMF, the EMF generated by the yellow phase is -5, and the EMF generated by the blue phase is -5, so the total EMF is 0. If you look here, the total EMF of red and yellow makes 10, and the total EMF for blue phase is -10. That makes up the EMF to be 0. If the load is not 0, you cannot design the system in such way. The delta connection is not possible. A three-phase system is symmetrical if each load has equal impedance value, the load impedance of each phase has equal phase angle, volt and current values equal for each phase, and the displacement is about 120 degree apart from each other. Oh, sorry about that. Now that we understand how three-phase alternating currents are generated, when it peaks, why it peaks, and we had a look yesterday on the rectification circuit. In this example or this diagram, we are looking into three rectification circuit that supplies to each phase, that we can now rectify the negative pulse and flip them into the positive pulse. So the ripple that is created by the three phases can now be reduced. So we already had a look at it in the previous lecture, so we're not going to go into detail about that now. So this is the summary of how the voltage ripple can be reduced by the usage of rectification circuit. A three-phase 6 pulses can reduce the ripple from 100% up to 14%, and if you use the 12 pulses rectification circuit, you can further reduce the kVp ripple up to 4%. So that is how three-phase power supply is made to an optimum power supply to an X-ray tube. Okay, let's move on to the other component of an X-ray tube and generator, that is transformer. Transformers are principal components in X-ray generator. Transformers are used to convert low voltage into high voltage for the X-ray tube, and from high voltage to low voltage for the filament circuit. This conversion is completed or done through a process called electromagnetic induction. Electromagnetic induction is an effect that occurs when the magnetic field is changed and alternating current is produced. So for the constant potential direct current, like battery, magnetic induction does not exist. So what is transformer? Transformers perform the transforming of an alternating input voltage into an alternating output. So it'll be input AC and output AC using the principle of electromagnetic induction. The generic transformer has two components. One is the wire or the conductor, insulated wires, and second is iron core, and this wire is wrapped around the iron core. An input AC power with voltage and current produces oscillating electrical and magnetic fields within the iron core. Before we go into detail about transformers, I just want to point out to not confuse electromagnetism with electromagnetic induction. Electromagnetism refers to the creation of magnetic force using electrical current, while electromagnetic induction, creating electrical current using magnetism. Alright, so they are two different things. As current traveling through a wire, it creates magnetic field around it along the axis of the loop. So along the axis of the loop, it creates magnetic field. The direction of the field inside this loop can be found curling of your right hand finger. The thumb points into the direction of the magnetic field. So if I have if you take your right hand and point your thumb to the magnetic field flow, then you would know that the current is curling from a clockwise motion or view or field. So in this situation, as current increases, magnetic flow will also increase around it. The basis of working principle of a transformer. A voltage transformer can be think of as an electrical component rather than electronic component. Transformer basically is a static electromagnetic electrical device that works on the principle of Faraday's law, as explained earlier. The transformer does this by linking more electrical circuit, not just one but two or more electrical circuits, and providing oscillating magnetic circuit that is produced by the transformer itself. This is what is called as mutual induction. Mutual induction is the process by when the coil of wire magnetically induce a voltage into another coil that is close in proximity from one to another. Transformers are capable of either increasing or decreasing voltage and current levels of their supply without modifying the frequency. This is depending on the number of coils or the number of turns that are available in that circuit. So if two wires are close together with the same current flowing through them in opposite direction, as shown in this photo, the magnetic field between the two wires will be the sum of two separate fields. So they'll be doubled up, or the sum of the field. However, by adding more will increase the magnetic field around the wire or the core wire. So that is the basis of how a transformer is designed. So basically, a wire is looped or wrapped around an iron core and creates many parallel lines of electrical wire. So when an electrical current passes through long hollow coil of wire, there'll be strong magnetic field inside the coil and will be weaker outside the coil. The lines of the magnetic field pattern run through the coil and spread out from end and go around the outside of the other end. So you'll get the field of magnetic field around the coil. the iron core of a transformer normally is a complete ring of 2 coils. So this is an example of just 1 coil. So normally it is a set of 2 coils. One is connected to a source of electrical power, and the other is the one that is connected to the electrical power is called primary coil, and the other supplies the power to a load or to another circuit, and this is called a secondary coil. The magnetization due to the current flow in the primary coil runs through the ring or the iron core and induce electron movement and current flow on the second coil. There is no electrical connection between these 2 coils. However, they are connected only by the magnetic field in the iron core. So if this is the iron core, the magnetic field that is filled or created by this coil that is connected to a power supply can be filled by the coil on this end. The moving magnetic field will induce a movement or the movement of electron that will then generate current flow. So this is an example of a transformer with this is a step-up transformer with the wire winding up an iron core, and there is a steady magnetic field that flows around the iron core, and this magnetic field induces the movement of electron in the secondary coil and generate current. When there is a steady current in the primary coil, there will be no effect on the secondary coil, but there is an effect in the secondary if the current is changing. A changing current in the primary coil is induced by EMF, electromagnetic force, in the secondary coil. If the secondary coil is connected to a circuit or to a load, then it will generate a current flow. So therefore, through AC supply, let's say we're working on a 3-phase AC supply, when there is a changing voltage to the power supply applied to the primary coil, the EMF, electromagnetic force, generated by the primary through Faraday's laws and whatnot, and then it will generate magnetic fields, and that will induce voltage in the secondary coil, and this is also fulfilling the Faraday's law. The rate of change of flux governed by the number of turns within the secondary circuit or secondary coil. So if we are working on 50 Hz 240 volt power supply, the polarity will change 50 times because there will be 50 cycles of sinusoidal wave coming in, and the change of polarity will then change the magnetic field. Change magnetic field will induce the movement of electron or induce electron movement and generate current in the other directions in the second coil. So the key here, a moving magnetic field due to the alternating current power supply at a specific frequency causes electron to move in the secondary coil, and this changing of magnetic in a way generate current in the secondary circuit. So how does a transformer work as a step-up transformer and a step-down transformer? Step-up and step-down transformers are very useful devices. with this type of device, we can multiply or divide voltage supply in an AC circuit. The transformer made a long transmission of electrical power possible. Actually, without transformer, you cannot deliver AC in great distance. A transformer that increases the voltage from primary to secondary coil is called a step-up transformer. Transformer that is designed to reduce the voltage from primary to secondary is called as step-down transformer. Step-up and step-down transformers are used extensively. The common use is the conditioning of electrical power for long distance transmission. So how do we get power supply at our homes, for example? So electric power is expressed as P equivalent to VI, V being voltage, I is current. The wire that we use to transmit electricity is transmitted over long distances. With distance, it might lose energy. So as a result, a step-up transformer is used to maximize the voltage. And for this reason, power supply do two things. First, they use step-up transformer to maximize the voltage, and then when the power supply has reached residential neighborhood or area or industry, they use step-down transformer to reduce the voltage at a usable power point for distribution. However, that only works, so 100% of efficiency only works if there is no power loss. So power out equal to power in, so therefore power in the primary coil should be equivalent to power in secondary coil. So the VI in the primary shall be equivalent to VI in the secondary. So let's assume transformer that we are going to discuss today working at 100% efficiency. So let's take in consideration of a step-up transformer. So say that a transformer has two coils, with primary coil has 200 turns, or in this example the primary has 1 turn and the secondary coil has 1000 turns. The voltage applied is 240 volt. Means if the primary is 200, the secondary is 1000, the voltage at the secondary is multiplied by 50. So if the example is as displayed here, 1 turn at primary, 1000 at the secondary, the voltage supply is multiplied by 1000. So it can be used either way. So if you have 1000 turns at the primary coil and have 200 turns at the secondary coil, then you would have a reduced voltage at the secondary circuit. So high voltage step-up transformer used to supply X-ray tube or to supply the potential difference between cathode and anode, and low voltage step-down transformers are used to supply power to the filament circuit in the X-ray generator. So what is the requirement of an X-ray tube and generator? First, it requires a direct current. We already know what's that. And it can only conduct and work in one direction. Cathode shall be negatively charged, and that's where the thermionic emission occur, and it boils off electron, and electron will be accelerated to the positively charged anode. Therefore, rectifiers or rectification circuits are needed in X-ray for X-ray tube and generator to function so that the AC can be converted to DC. And what else do we know? We know that the potential difference between cathode and anode occurs from 50 kV up to 150 kV. So to increase the voltage supply, we can use transformer. In this case, a step-up transformer. An ideal transformer is a transformer that works without power loss, meaning that power in the first circuit, the primary circuit, and the secondary circuit shall be equal to 0. The number of turns of the coil is normally termed as N, so in this it could be NS as number of turns in secondary coil, or N1, N2, so you can name it anything basically. Now that we understand how transformer functions, we can quantify the variables. So the total voltage induced into the secondary winding of the coil is determined by the ratio of the number of turns in the primary to the number of turns in the secondary, and also by the voltage applied to the primary coil. And what I mean by that is the total voltage induced in the secondary winding is mainly determined by the ratio of the number of turns in the primary coil to the number of turns in the secondary coil, and also affected by the voltage applied can be simplified here. You can calculate if a transformer is a step down or a step up by simply looking at how many turns are there in the primary coil and how many turns are there in the secondary coil. So this is given as in this equation. This is an example of the primary coil has more turns, more number of turns compared to this secondary coil, and we can tell this is a step down transformer. And if an alternating current is applied to this coil as a circuit, the magnetic flux can be filled through the iron core and induce current flow in the secondary coil. Say there are 200 turns in the primary coil and 120 number of turns in the secondary coil, and the voltage supply at the primary is 120. Sorry, number of turn is 50, and this is voltage and voltage. And from the calculation we can get that the voltage at the secondary circuit is 30 volt. So from 50 it is now, from 120 it is now has reduced to 30 volt. So it is a step down transformer. Ratio is always expressed as primary to secondary. The ratio does not indicate the number of turns, but rather the ratio. Okay, that basically concluded the main components of an X-ray generator that involves a step-down transformer, a step-up transformer, and rectifier. So let's have a look a little bit more on the control panel or the console that controls the kVp, tube current, and exposure time. The maximum energy of an X-ray can be generated in the X-ray tube is depending on the set kVp. So I've said this earlier in the previous lecture. The maximum kV, say 120 kV, the maximum energy for the electron is 120 keV, thus maximum energy of X-ray photon is also 120 keV. So the maximum energy of an X-ray in the beam is defined by the kilovoltage set at the control panel. The greatest number of photons is emitted with energy normally at 1/3 of the maximum energy. The reason is at setting your kVp to 120 kVp means the probability of the electrons to have energy at 120 keV is very low. Most of the electron would have 1/3 of the set maximum kV. So if the power supply is 120 kV, most of the electrons would have 1/3 of the energy. So most of the electron would have at about 40 keV, more or less. So although you set it to 120 kV, the produced beam is normally at the greatest number, or the highest intensity is normally produced at 1/3 of the maximum energy. So this being the example, the voltage is 150 and the peak, the highest peak of the Bremsstrahlung is at 50. And if you set at 100 and the peak is at lesser than that, and this is the characteristic peak. It is unique to the binding energies of the target anode. So because the binding energy is more than 40, if you apply kV less than 40, you would not be able to see the characteristic peak. So but we are going to have a look at this in the second topic, where we are going to see what affects the different spectrum of X-ray. We also had a look at the difference between single phase power supply and three-phase power supply. Because of the steady power supply supplied by the three-phase, even much better with three-phase with 6 pulses rectification or with 12 pulses rectification, the steady voltage waveform will produce a higher intensity of X-ray. So these two peaks are similar, or the spectrum looks similar, with the peak, the intensity peak at almost from 50 and slightly higher, 60 for three-phase power supply, but the characteristic remain the same, because that's only unique to the anode target, has nothing to do with the single phase or triple phase power supply. But the intensity, look at the area under the curve. The intensity of a three-phase power supply is an abundance or superior to the single phase power supply. So in a way, we can summarize that three-phase power supply produces X-ray beam with higher intensity with an optimum energy higher. So the optimum energy here is about 50, 60 say, but this is at 50. So the energy, the optimum energy is higher, the intensity is higher. As a general rule of thumb, operation on three-phase equipment is at about 12% better than of a single-phase power supply. Due to the higher intensity, higher penetrative power due to higher optimum energy produced by a three-phase power supply X-ray generator, we can reduce the exposure time to the patient in producing a good quality diagnostic images. So therefore, patient dose is also significantly reduced, as we are using three-phase 6 pulses power supply, and even better when you're using three-phase 12 pulses power supply. And what else do we know and we do understand from the lecture? The tube current in the first lecture governs the number of electron that will be boiled off the cathode filament. Therefore, higher current will produce or boil off higher number of electron, thus increase the chances of X-ray being produced via Bremsstrahlung or characteristic radiation. So in short, the intensity of an X-ray produced increase with the increase of current setting. So if you can see here, the KVP is set for both the parameters. However, the current is higher for the red compared to it's double up, and the intensity is double up. But as you can tell, because the KV is the same, let's say these are both using three-phase power supply, so it's not affected, and the optimum energy or the effective energy is the same for both. The only thing that differ is the intensity. So intensity is closely related to the set tube current. So higher current setting will increase the intensity and will not change the energy or the effective energy of the beam or the maximum energy of the beam. So 2 MA, for example, has 2 number of photons, or 4 MAs has 4 numbers of photon. This is just a factor, not literally 2 or 4. Tube current and time describes MES, or the product of tube current in milliamperes, and exposure time set describe the number of electrons that will be bombarding the target in a second. So let's compare these three spectrums. This X-ray tube has been set to a KVP 95. The effective energy for the three spectrums are the same. The characteristics are also the same, because characteristic is unique to the target. We don't exchange any target, and this is unique to the KVP setting and the type of power supply, single phase or triple phase. The only difference that you can see here is the current, and well, let's say we use it at different time and it generate different MES. So the intensity differ with different tube current with time. In practical terms, ampere is a measure of the amount of electric passing a point in an electric circuit. 1 ampere is equivalent to 1 coulomb per second. So 1 ampere is constituting to 1 coulomb per second. 1 coulomb has at about 6.25 by power of 18 electrons. 1 electron has 1.6 to power of 19 coulombs in a second. So what is the number of electrons in 1 MES? 1 MES is equivalent to 10 MA times 0.1, for example. So 10 MA current set at 0.1 second exposure is equivalent to 1 MES. How many number of electrons are there? So you can give this a try and try to calculate the number of electrons. Then you know that as you increase current or time, the number of electrons will also increase. As the number of the electron increase, there'll be higher probability that this electron will hit the anode target and produce X-ray. Therefore, increase the intensity of the X-ray beam as the current increased or time increased or MES increased. In summary, this is the whole components that we have already looked at. We have got the X-ray tube, X-ray generator, rectification circuit, transformer, AEC, the filament itself, the focal spot, how the filament affect the effective focal spot, anode hill effect, anode target. So this is a good diagram to summarize the whole lecture on topic 1. So that's concluded the whole discussion or explanation on topic 1. Of course, as you do your own revision and your own study, you will discover more. So in general, I just want to end this lecture by showing to you what a generator looks like, and everything is normally encapsulated in a box. So this is what the high voltage generator looks like. It can be behind a wall in a specific room and with all the wire supplies and everything. So that's what it looks like. And then you have an X-ray tube with a collimator, and I did not touch much on collimator because we are going to have a look at that in a different chapter, where we are going to have a look at how collimator affect field size and so on. But in brief, we can understand that collimation will define the field size. So the collimation can be adjusted, so there will be a light or guidance visible light that will be used to guide the field size, and that will adjust the size of the beam. So if you open your collimator to be bigger, you'll get bigger field size. Then you can feel the ununiform hill effect caused by the X-ray tube and so on. And you can also expose unnecessary dose to non-region of interest and so on. But we'll talk about that more in the lectures. Alright, now that we are done with, I'm done with topic 1 in terms of the lecture. On your end, I'm expecting students to do own revision on topic 1. These notes will be provided on e-learning, and you can always refer back to the recorded lecture for clarification here and there. Based on your own revision, at 11 a.m. on Tuesday, next week on Tuesday, in respective groups, students are required to hold a formal discussion to discuss several questions for class activities. So the idea behind a class activity is for the student to acquire knowledge by not just listening, but perform a creative or higher order thinking skills, and perform all those to make sure the knowledge acquired is understood and the students are able to deliver information based on your understanding. So based on your formal discussion, take a screenshot of photos. If you hold the meeting through Zoom, Meeting Place, Google Meet, Webex, you can hold the meeting via WhatsApp, Skype. Choose your own means. For as long as you can take a screenshot or a meeting shot or a chat shot, forum shot on your meeting on topic 1, and post that to my email address. This is the official email address for ZCT534. So for any activity submission, you can submit to this email address. On the same day at 12 p.m. we will meet via Webex. So during this Webex meeting, students and me, among students itself, will perform two ways communication activity concerning topic 1. So you will be delivering your answers based on discussion held in your group, in your respective groups, and then I will be doing the assessment based on your presentation. Other students are allowed to to ask questions or deliver feedback based on your presentations too. These are the details of the WebEx meeting. You can take note on that. So we'll be meeting from 12 until 1 so that we can perform the two-ways communication class activities on topic 1 during this meeting. These are the groups that I have randomly selected via grouping tool in e-learning. So if you do not know who are your group members, here are the email address. Some have actually furnished your details with telephone numbers and so on. So here are your group members. Each presentation, it's up to your creativity on how do you want to present your answers. So each presentation will be evaluated based on the confidence and the content. So these are the important aspects that will be evaluated based on scale 1 until 5. For example, in topic 1, we'll be doing a group activity. So students will be assessed by group. If in other topics we say that we perform an activity individually, so student will be assessed individually. So this will make up to your 10% presentation marks for your assessment. So there'll be more than one presentation, there'll be more class activities. So it's in a good way, as you do your own revision, you acquire more deeper understanding on the topic, and you at the same time can get good marks if you deliver good presentation or good answers to your class during class activity. These are the questions set for topic 1. So there are 5. You are required to discuss in your respective groups the answers or the discussion or explanation of these 5 questions. So have a look at these questions and get into your groups and start the discussion. I don't respond students individually on WhatsApp sometimes because I believe all the questions are good, but it's better for me to answer the questions via in a way that everyone can listen to the answers. Some were asking for the reference. These are the list of references that you can use, and I don't stop here. You can use any other references. By all means, choose your most preferred reference book or text, but these are the suggested references, so you can use this. Alright, there is also a comment by a student saying that if they are not able to catch up, or maybe my pronunciation is not clear enough, I'll go too slow or too fast, or whatever it is. On YouTube, you can click on CC and it will allows your YouTube to display captions or subtitle to the presentation. I'm not saying all the captions are 100% correct, but they are at about 80% correct, so you can use that as a guide. and in YouTube recorded lecture I do speak quite slow. You can increase the playback speed up to 1.20, 1.25 or 1.5 for a much more pleasant delivery. The reason why I speak quite slow is because I do not want to mumble words. I do not want to eat words. So I do want to make sure that I can get the idea or get the information across as clear as possible. So that was the aim. So you can always increase the speed. So that's concluded everything on topic 1, where I'll post again future lectures on topic 2, and we'll stay updated. See you guys next week on Tuesday. Thank you.